Good afternoon. Welcome to the next lecture of the heat transfer. I am dealing with the unit number 4, heat exchangers in the heat transfer theory, which is 16 ME 63. And this particular topic is very interesting, and I should say that you can bet 19 out of 20 in any of the exams. Okay, why it is so? I will explain the later stage. So let us start the topic. First we'll have the definition, the classification, then terms involved, then one derivation, as well as the last one we'll have the few numericals. Okay, fine. So whatever the sessions allotted to me are like this one. So today we'll start, and remember we'll be referring to the, whenever I say data handbook, it will be of 6th edition. Okay, if you have got the 7th edition or the 8th edition or even maybe the 9th edition, then refer corresponding pages. So whenever I say data handbook, it is necessarily the 6th edition. Please remember. Okay, then the pages which are there for this particular topic, that is unit number 4, is page number 151 to 175 of the 6th edition. So please correct yourself whenever you are talking about your data handbook. Okay, fine. So let us start. So now let us start the definition. But before that, I want to explain the concept. If suppose a person A calls the person B through the telephone, then how will call? So it is not direct, but it is through a particular intermediate, you can say a body, what is called as a telephone exchange, or let me say just exchange. Means what? Whenever I want to exchange the ideas, I need some means to do it. I need some means to it. Without this one, this contact is not possible. In the same way, whenever the heat is to be transferred from the one fluid to the another, like this one, you require a particular device which is called as a exchange. Since it is called as, since it is exchanging the heat, we call it as a heat exchanger. Okay, but the difference between, in this case, the both way it is possible. So A can give the idea to the B, and B can give to the idea to the A. In the same way, but whereas when I talk about the heat exchangers, it is not possible in two way, but it is possible from the only one way. That is nothing but only the hot fluid can give out the heat to the cold fluid, not in the both ways. That is the major difference. Okay. Now, if we go for the definition is given to you. Okay, then it is basically through the solid barrier. Then it is widely used in HVAC, that is heating, ventilating and air conditioning, power plants, then chemical plants, all refineries, etc. This etc. is little bit very large, because you can name any of the industries, it will involve this particular device, what is called as a heat exchanger. You can name any industry, it will surely involve the heat exchanger for sure. Then next one, we are talking about the classification. There are n number of the classification, but first based on the function. The first function is called as a recuperative type, which is the most commonly used. Means what? Both fluid will be flowing simultaneously. Then second one is called as the regenerative or the storage type, which is used in the solar heating of the homes. Then next one is the direct mixing type. This is rarely used, but however, the heat exchanger like the cooling towers falls into this category. But however, in our cases, mostly we are dealing with only the recuperative type, mostly. Okay. Then next one, the next classification is based on the flow direction. So in the flow direction, we have got the parallel flow, in which the both fluids means what? It is possible to have a heat exchanger with the n number of the fluids, more than the 2 also, but in most of the cases we will consider only 2. One is hot and one is cold. So I will say the hot fluid as a cold fluid, if both are moving in the same direction, means they are entering into the heat exchanger in the same direction, living in the same direction, then it is called as a parallel flow. But if one of that is opposite, but both fluids will flow in the opposite direction, it's called as a counter flow. Then if they are going in a perpendicular way, then it is called as a cross flow heat exchanger. Then next one, it is based on the flow arrangement. So it can be a single tube. Okay. The next one is shell end tube. Okay, then single pass means what? In the both shell as well as the tube are going in 1:1, then the multi-pass is N:M. So N is in the shell and M is in the tubes. So in general, N will be 1, 2 like that, whereas M will be 2, 4, 6, 8, 12 like that. That will be taking the later stage. Okay, the next one what we are dealing is nothing but this particular diagram. So there are n number of the heat exchangers we have shown. So this is a single tube parallel flow. You can see. So hot fluid is in the tube, and whereas the cold fluid is in the outside. Okay, but see, please, both are moving in the same direction. Therefore, it is called as a parallel flow, because it is a single tube parallel flow, whereas this is single tube counter flow, whereas the tube is one, a hot fluid is going from the left to right, whereas the cold fluid is going from the right to left. In the similar way, in other configurations also you can see, if I talk about this one, as you can see, there is a single tube cross flow, because fluid A is going in this direction, fluid B is in the in direction. But very importantly, please remember, one of this should be hot and one of this should be cold. Means what? This heat exchanger is used to extract the heat from the hot fluid, whereas or the other way, it is to give up the heat to the cold fluid. Okay, so please and refer page number 157. So 157 data handbook, obviously it is 6th edition, for TEMA notation. So TEMA stands for the Tubular Exchanger Manufacturer Association. When you go for your career as a heat exchanger design or in the real practice, this TEMA course will be very much useful. Okay, fine. Now we'll have the few questions. Anybody? Sir, there are so many heat exchangers you have spoke about, but which are more important? Okay, fine. Or which are more popular, which are more used? The next one, what are the common terms used? Obviously, whenever you are talking about the exchanger or any device, it is necessary to have the different terminology. Okay, and third one is, what are the equations used for the analysis? Yes, all these three will be the core of the syllabus. Okay, fine. So now the most important, rather we'll say mostly used, are first one is a parallel flow. Okay, let it be a single tube, multi-tube, whatever is there, but the flow arrangement or flow direction will be very important. If you see here, so cold fluid is going from this one and exiting by this one, whereas the hot fluid is going inside the tube. Okay, the similar hot fluid is being cooled and cold fluid is being heated. And now since they are moving in the same direction, okay, that what we call as a parallel flow. In the similar way, the counter flow, whereas the hot fluid is going in the left to right direction, whereas the cold fluid is in the other direction. That is called as a counter flow. Where the these two are related to cross flow, where there are either unmixed or mixed flows. Okay, so these are the common things what we are using. First of all, what is most important is the flow. Whether it is a parallel flow or the counter flow is the most important question for my analysis. Okay, now let us go for the next terms used in the heat exchangers. What are the different terms we are used? First one is the heat duty. Obviously, since it is used to exchange the heat between the two fluids, so therefore heat duty is necessary to define. Okay, the definition is given to it is nothing but the amount of the heat that can be transferred from a hot fluid to the cold fluid over a unit amount of the time, and which is measured in the watt, kilowatt, or whatever is there. Then these are given by the three equations. Okay, now what is this? It is the QH equal to MH CPH into THI minus THO. It is just something like that, MCP delta T, whatever you might have studied in the ATD or the BTD, the same way. Now what is this MH? It is the mass flow rate of the hot fluid. H stands for the hot fluid. Okay, then CP is the specific heat at constant pressure then of the hot fluid. Then THI is the inlet temperature of the hot fluid, and THO is the outlet temperature of the hot fluid. In simplest term, this first term or first equation gives the idea about how much heat is lost by the hot fluid. I repeat, how much heat is lost by the hot fluid, whereas the second one is given as a MC CPC into TCO minus TCI. So what is MC? Once again, the mass flow rate of the cold fluid and specific heat of the cold fluid, and this is the outlet temperature of the cold fluid, and this is the inlet temperature of the cold fluid. But very importantly, few things to remember. Remember, this mH stands for, mH is being measured in kg per second. Sometimes in measurements, you may be remembering in your heat transfer lab, you measure in terms of liters, but later you need to convert in kg per second. This is in joule per kg Kelvin. Okay, whereas this can be either in Kelvin or degree centigrade, and since the radiation is not involved, you can obviously choose this one in the degree centigrade without any hesitation. This is the heat lost by the hot fluid, whereas this is heat gained by the cold fluid. Okay, for the ideal consideration or ideal case, the QH should be equal to QC. That is, whatever this is lost, the heat lost by the hot fluid should be equal to heat gained by the cold fluid. This is ideal case. Okay, then the third equation what we are doing here, that is Q equal to UA LMTD. This is called as a heat duty equation. This is hot fluid, heat lost by the hot fluid, heat gained by the cold fluid, but whereas this is a heat duty equation. Q equal to UA LMTD. Remember, you calculate for any of the ideal cases, 1, 2, 3 equations should be same. Now question comes, what are these terms? As you say, it is a UA LMTD. What is U? U is the overall heat transfer coefficient, which is given as watt per meter square Kelvin, and area A is the surface area of the heat exchanger in meter square. Generally it is given as pi dl. D can be either inner diameter or outer diameter. If it is the inner diameter, then it is a inner surface overall heat transfer coefficient. If it is the outer surface, then it is called the outer surface overall heat transfer coefficient. Alternatively, it is called as overall heat transfer coefficient based on the inner area, if it is pi DIL and pi D naught L. Then last one, most important, is called as a LMTD, which is called as a logarithmic mean temperature difference. Then the question comes, sir, what exactly these terms means? Okay, area I won't talk much, but let us go for the next one. Okay, so first one, overall heat transfer coefficient. Remember, whenever the heat exchanger is under working, two fluids are flowing. Okay, then whenever the hot fluid is flowing, then the fluid is flowing, and hence it will be involving the convection. Then cold fluid will be also involving the convection, and the barrier will be there, therefore it will be involving the conduction also. So involving all these terms, okay, involving the resistance of all this one. This is a, let us say, for the outer fluid, this is for the inner fluid, this is for this is the conductance resistance. All if we involve, what it comes is nothing but the overall heat transfer coefficient. See the equation. Equation is 1 upon U naught equal to this much. Okay, so you can please refer the page number 151, 155, 156 for all these equations. Okay, now question comes, sir, what is this one? This is, as I told, if it is based on the inner surface area, it is a UI AI into delta T. Delta T is not just delta T, but rather we will say the logarithmic mean temperature difference. I am coming to that after a few minutes. Then this is nothing but the based on the outer surface area. Okay, in both cases, okay, Q should be equal to this one, and thus what we can say, delta T and delta T will be the same. Thus what we can say, UI AI equal to U naught A naught. Now question comes, how to find out the U naught? This is the equation. Okay, once again please refer to this one to have that particular equation. The next one is called as a LMTD. Now question comes, what is the LMTD? It is the logarithmic or the log mean temperature difference, which is the average of the temperature difference between the hot fluid, okay, hot and cold fluids at the each end of the heat exchanger. Now question comes, sir, why it is so? Why we are taking this logarithmic mean temperature? Okay, now for that let us take one small example here. Okay, fine. Now let us say this hot fluid is being cooled from 80 degrees centigrade to 60 degrees centigrade, where the cold fluid is being heated from 20 to 40. Now question comes, where this heat transfer is taking place, whether at the one end or the both end? Obviously not, it is going throughout the length. That's why we are going for that logarithmic mean temperature difference. The derivation will be follow. Now the meaning is that the heat transfer takes place, or the temperature difference lies throughout the length of the heat exchanger, throughout the length of the heat exchanger. Okay. Now we are going for the what exactly the meaning is, that the LMTD is nothing but the driving force. It is the driving force for the heat duty of the this heat exchanger. Okay. Now how it is given? LMTD is given by theta 1 minus theta 2 divided by ln of theta 1 by theta 2. Now what is the theta? Theta, as you know, it is nothing but the temperature difference. Hope you all done in your the fins also. In fins you have used d square theta by d square, like that. So theta is nothing but temperature difference. So temperature difference at the inlet, okay, and temperature difference at the outlet. If you know this, then you can find out. Now why it is called logarithmic? Because this term this expression will have this logarithmic term. Now how it comes, we are going to derive, don't worry about it. But however, the question comes, sir, what are the notations that we are using? Okay, that's a good question to be raised. So suppose the hot fluid and cold fluid. For hot fluid at the inlet and at outlet, so it is the THI and this is THO, then this is TCI, then this is TCO. Okay. Now for a parallel flow, the difference between these two, it is called as a theta 1 and this is called as a theta 2. Okay. For the moment I am dealing with the parallel flow only. Later on we will going for the counter flow. Okay. Sometimes this is called as a delta T also. We can use either theta 1 as or theta 1 and theta 2, or even it is used as a theta I and theta naught also. Theta I is nothing but the temperature difference at the inlet and temperature difference at the outlet. Now whatever I have written, it is applicable for the both counter flow as well as the parallel flow. I repeat, this equation is applicable for both counter flow as well as the parallel flow. And remember, few page number here, 151, 155 and 156. Okay. Then the question comes, so there are certain terms called as the RFI and RF naught. What are those? Yes, very good. So these are called as a fouling resistance. Fouling resistance are also called as a fouling factor. Okay. Many times we used to say what is true in lamplight may not be true in sunlight. Means what? If the heat exchanger is used to cool a particular oil or something hot fluid from one temperature to another temperature, but actually we are going to get less than that. Why? So these are the some reasons for that. Now what exactly this one is? It is nothing but the fouling factor. Remember, as the heat exchanger is put into the service, its surface is going to deteriorate, or the performance is going to deteriorate with respect to time because of the deposits, of the heat transfer surfaces. Okay, such layers will reduce the areas, or what I can say, it will increase the resistance. Since they are solids, they will offer a conductive resistance, hence that will be added. Okay, and it depends upon the type of the surface as well as the type of the fluid. Okay, so whatever the RF fouling resistance given by the water to the copper may be totally different from than the other surfaces. Okay, in that case, please refer to the data handbook page number 156, where the different listing of different values of the fouling factors have been given. Now why it has been given? Because when if suppose in exam it is asked, okay, what is fouling factor, don't write only the definition, write at least one or two examples which are there in your data handbook. That is the meaning of it. Okay, that is the fouling factor. But unless otherwise specified, we are not including this RFI and RF naught. We are not including those things into the picture. Okay, so if I say a heat exchanger is working and these such values are not given for the preliminary examination or the estimation, you can neglect it, but for the exact you need to consider. Okay. Now another questions come here. So why it is the A naught by AI? Why it is not A naught by AI? Because this is the overall heat transfer coefficient based on the outer surface area. Outer surface area. Therefore, it is given as 1 upon U naught equal to 1 upon H naught plus RF naught plus so and so. So wherever the inner surface resistance are involved, so we have taken this ratio, that is A naught by AI ratio. Suppose if I want UI, 1 upon Ui, then what will the equation? Equation is the same, but wherever the i's are there, that will be free of the ratio area of the ratio of the areas, but wherever the outer surface resistance are there it will be included. So once again, please refer to this page number 155, I suppose, where both the equations have been given. So whenever the overall heat transfer coefficient is being asked, please don't forget to mention even the equations. Even the equations, please don't forget to mention it. Okay. Now, okay. Now question comes LMTD for the parallel flow heat exchanger. Now, as I told few minutes back, okay, just a minute. Okay, as I said, the parallel flow, the LMTD is given by theta 1 minus theta 2 divided by ln of theta 1 by theta 2. I said theta 1 and theta 2 are temperature difference at the inlet and outlet respectively. Now the question comes, sir, yes, you have told this equation, but what is the proof that this equation is right? Yes, if that is your question, it is a very good. Okay. Now, how it comes, we are going to derive it. Now the question comes, sir, what exactly the derivation is there? What exactly derivation is there? Well, derivation is nothing but the process of going to a unknown station from the known, or whatever your destination is there, from the known factors we are going to reaching it. Okay. So in this case, what is unknown? The LMTD is unknown to me. Now question comes, what is the known? I know what is the temperature. Okay, I know temperature at the inlet, at the outlet, for the hot fluid as well as the cold fluid. I know what is the area, everything I know, but I don't know with respect to this one. So I am finding out the derivation for this one, and for derivation certain assumptions are required. Now question comes, sir, what are the assumptions? Yes, there are 5 assumptions, starting with the heat exchanger is insulated from the surroundings. Means what? I am not allowing either the convection or the radiation at the outer surface. Okay. So whatever heat is lost from the hot fluid, it should come only to the cold fluid. That's all. The next one, axial conduction along tube is negligible. Okay. Next one, potential and kinetic energy changes are negligible. Okay, the meaning is that whenever we are taking any particular fluid under motion, under flow, obviously it will have the certain kinetic energy. Those kinetic energy will be very small compared to the heat transfer. Means what? These are very much negligible. The next one, the fluid specific heats are constant. This is a reasonably assumption which doesn't hold in an actual position. Why it is that? Because whenever you are talking about any properties, it may be the density, viscosity or anything which is surely affected by one or the other factors. Okay. So in heat exchanger, the major factor which is coming is the temperature. So we are assuming that the specific heats are constant. So whatever the temperature, whatever may be the temperature, if I say the specific heat of this fluid is let us say 3.2 kilojoule per kg Kelvin, then it is 3.2 whether it is at 80 degree centigrade, 60 degree centigrade or 50 degree centigrade. That is the meaning. The overall heat transfer coefficient is constant, which is nothing but the another way of expressing, saying that the fluid properties are not going to change with respect to the temperature. It is going to be same. Based on that, we are going to have the derivation. As I told, so I want to know the expression of the LMTD, or it is also called as a delta TLM Okay, and the same thing can be given as a delta T1 minus delta T2 divided by ln of delta T1 divided by ln of delta T2. Okay, so before I start this one, the question comes, sir, whether it should be in degree centigrade or Kelvin. Okay, and whenever I say U is in watt per meter square Kelvin, obvious question comes, sir, whether this should be in Kelvin or degree centigrade. Remember, when I say it is the temperature difference, it obviously tells that whether it is a Kelvin or degree centigrade hardly makes a difference. But still, let me clarify you. Question comes, whether the radiation is involved here. Answer is no. No, radiation is not considered any of this one. The first assumption says that only. Hence, once the radiation is not involved, you can with confidence can use the degree centigrade. However, you are free to use the Kelvin also, but I will suggest you to use only the Kelvin. Oh, sorry, I will suggest you to use only degree centigrade. Kelvin can be used, hardly it makes any difference on the answer. Please note this point very clear. Okay, now let us try to find out the derivation. Okay, now this is the our parallel flow. Why it is parallel flow? Because the hot fluid is going in this direction and cold fluid is also moving parallel to it. Therefore, we are telling it is a parallel flow, and this is the heat transfer surface area. And as you can see, there is a insulation is there. Therefore, whatever the heat transfer is there from the hot fluid, it should reach only the cold fluid. Only the cold fluid. Now, what is this? This is the temperature at any point, and this is the section what we say as a dx. Now, if I draw the temperature profile, it will look like this one. Okay. Now, see, this is the hot fluid, where the hot fluid is being cooled here. Okay, this is the inlet temperature and this is the outlet temperature, whereas for cold fluid, this is the inlet temperature and this is the outlet temperature. Now, what we are going to do? We are going to derive. Derive means what? We are taking a random section, let me say dx. Now, dx is a differential element. For that, we are deriving it. Okay. Now, question comes, whenever we are doing it, we are going for the dx. For the dx, what will be the heat transfer rate? If the total heat transfer rate is the Q, then the differential heat transfer rate will be dq. Differential heat transfer will be dq. So, first we will find out the answer for the dq, then we will go for the integration. That I say that from the known to the unknown. From the known to the unknown. Now, question comes, what is this delta T1? It is at the inlet. So, this is THI minus TCI will give the delta T1. Correspondingly, DHO minus DSCO, that is outlet temperature of the hot fluid minus outlet temperature of the cold fluid will give the delta T2. Okay. Now, what is this TC? Temperature of the cold fluid at any section of the heat exchanger. At any section or at any length of the, say, this is the TC. Okay, then what CC? CC is nothing but the heat capacity. Okay, this CC is nothing but MC into CC. That is, the heat capacity of the cold fluid is equal to mass flow rate in kg per second, and this is in joule per kg Kelvin. So, this is heat capacity. Either I can use this one or this one. Similarly, the CH will be MH into CH. Okay, this is for the hot fluid. Okay, at any point, if I take, please wait for a minute. So, at any section, what will the temperature of the hot fluid? It is TH. At any temperature, it is TC. Therefore, what I can say? It is the delta T. Okay. So, at delta T, at inlet, I will write THI minus TCI equal to delta T1. Then, similarly, THO minus TCO should be equal to delta T2. Okay. Hope you have drawn this figure, then we will start. You have got 2 minutes to draw this one, then we will start. Otherwise, you have got a slide, you can draw it later, pausing the video. Till then, let me write the few things. Okay, I hope you have drawn the figure. So let us see what we have. First we have got the Q equal to U A delta Tm, or what we say, the heat transfer rate or heat duty equal to the overall heat transfer coefficient times the area, surface area, into delta Tm, that is LMTD. That is LMTD. The next one, what we have got, QH equal to, okay, it is the MH CH into THI minus THO. Similarly, QC will be having MC into CC TCO minus TCI. Okay, and due to the assumption 1, what is the assumption 1? Please see the slide. Okay, in slides it is given that due to the first assumption, that is the heat exchanger is insulated, means the QH equal to QC. Therefore, I am writing this one. But please remember, I am talking about only the differential element of dx. So I am going to draw for this one only. Okay, this is the this is THI, this is TCI, this is THO, and this is TCO. Okay. Now, if we write the differential, the heat, okay, so how we can write? It is minus MH CH into DTH. Now, question comes, sir, why I have written the minus? Okay, let's see. If I move from the inlet to outlet, the heat, the temperature of the hot fluid is going to decrease. So if I say this minus this is nothing but the, okay, this is lower than this one. Therefore, I am using minus sign here. This is very much important in this derivation. Please try to understand. Let me explain once again. Remember, in the direction of the flow, the temperature at this and this one, if I take for the hot fluid, it comes to be less, obviously. So it is being cooled, means at the exit, the temperature would be less than this one, right? So for the same dx, it is very much true. Similarly, we write as a dq equal to mc cc dtc. Now question comes, what exactly this means? This is for the hot fluid and this is for the cold fluid. The meaning is, in this dx, whatever the heat is being lost by the hot fluid is something but the same as the cold fluid. Now question comes, sir, why you use the only D here? Okay, why not here? Remember, if I take a section, okay, the mass flow rate as well as the heat capacity itself cannot be differentiated, but the temperature, yes, it is obviously changeable. Okay, then these are the two equations. Similarly, what is the third equation we have got? It is the U, then delta Tm into dA. Okay, now what is this one? This is nothing but the third equation. Whatever we have written the overall equation in the initial stage, the same way it has been written. dq equal to U into delta Tm into dA. Now what is this one? It is the mean temperature difference, and we want to find out the expression for this one. U is overall heat transfer coefficient and dA is the differential area. A is the differential area. Before I proceed for the next step, okay, something from your mathematics. Okay, let me write here. Okay, so can anybody tell what is the integration of the ln x? Okay, it will, from the 1 to 2, it will be ln of x2 divided by x1. Hope all of you know it. In the similar way, if I can I write the same thing as a ln of x1 by x2 with the minus sign? I repeat, if I multiply this term by minus 1, then can I write ln of x1 minus x2? Is it possible? Yes. If you know this one, then the derivation is very simple. Okay, fine. Take this, then we'll start. So, as you know, this delta t is nothing but the th minus tc. Okay, so these are the differential form of our equation. In the similar way, what we have, it is the d delta t equal to d of th minus tc. So let us say it is equation number 1, 2, then 3, then it is 4. Okay, now we will write the equation for this one. So how I can write? It is the dth equal to minus dq divided by mhch. Okay, similarly dtc equal to dq divided by mccc. This is for hot fluid, this is a cold fluid. So for this temperature of dTH, what will be the equation? Similar way. Remember, minus sign comes only with for the hot fluid because it is going in this direction and temperature is being decreased. Okay. Then next one, what we can write? Okay, take this one. So what I can write? It is the delta T should be equal to minus dq into 1 upon mhch plus 1 upon mccc. Now, what about this one? dq is nothing but this one. So, these are the knowns, and finally I want to know these are known. So, I am substituting this dq equal to u delta tm into dA in this equation. So, what happens? It is d delta t equal to minus u delta t into 1 upon mhch plus 1 upon mccc into dA. Now delta t is there from the variable separation. So what I can write? D delta t divided by delta t should be equal to minus u into 1 upon mhch plus 1 upon mccc into dA. Okay, this is for small element that we have shown. Now for the whole of the heat exchangers, we need to integrate it. Okay, so from inlet to outlet. Now question comes, what about this one? You can do this one, but even without doing it, it's understood that at the inlet the area is 0, therefore A2 minus A1 is as good as the integration of dA only. Therefore, as you see, the integration of delta t. So what will be that? It is the ln of delta t2 minus delta t1. Okay, let us say this is x, ln of x. Okay, so should be equal to minus u into 1 upon mhch plus 1 upon mccc into A. Okay. So this is equation number 5. Please take down till, I hope this is understood. Okay, if not, please go for the previous minutes of the video. You come to know why the negative sign is taken. Okay. Now, question comes, have we reached our goal? The answer is no. Okay. So, the question comes, how to find out it? Remember, you have written Q equal to MHCH into THI minus THO. Therefore, what I can write? MHCH equal to Q divided by THI minus THO. Similarly, MCCC can be written as Q divided by TCO minus TCI. Okay. Now, we have got two more equations. Let me say equation number 6 and equation number 7. If I substitute, what I will get? It is the ln of delta T2 divided by delta T1 should be equal to minus U, okay, then divided by, okay, Q will be in the denominator, the rest will be in the numerator. So, how it will be? It is a THI minus THO plus it is TCO minus TCI. Okay. Now, question comes, sir, is it the expression? No, you need to wait for another 2 steps. Okay. So, now the same, if I take this one, can I write THI minus TCI? That is nothing but the delta T1, and similarly minus of THO minus TCO is nothing but the, minus of THO. Okay, let me, it is the ln of delta T2 by delta T1 should be equal to minus U divided by Q. Okay, can I write like this one? THI minus TCI. Okay, then minus THO minus TCO. Right? Just by the rearrangement. Now, what this resembles? This is nothing but the delta T1 and this is delta T2. Okay, based on that, what we can write? Okay, let me take it once again. So, it is ln of delta T2 by delta T1 should be equal to minus U. Okay. Now, what is this? This is the delta T1 minus delta T2 divided by Q. Okay. Of course, the area is there. Fine. Now, see, here minus is there. So, if I can write Q equal to, I am taking this term into here. So, what will that? It is minus U, okay, into delta T1 minus delta T2 divided by ln of delta T2 by delta T1 into area terms. Now, since minus is there and as we have seen the logarithmic property, what I can write? U into A equal to delta T1 minus delta T2 divided by ln of delta T1 divided by delta T2. This is equal to Q. If suppose this Q is compared with UA LMTD, then what it means? This term, whatever we have derived, this is nothing but the logarithmic or the log mean temperature difference, which is given by LMTD. Let me write it once again. It is the delta T1 minus delta T2 divided by ln of delta T1 by delta T2. It is also, we can write in terms of the theta, theta 1 minus theta 2 divided by ln of theta 1 by theta 2. Okay. Now, please see. Once again I am repeating. So this delta T1 or delta T2, let it be in degree or Kelvin, but it should be consistent. So for all the cases, please take the things in degree centigrade only. In the degree centigrade only. So this is the derivation of the logarithmic mean temperature difference for a parallel flow. For a parallel flow. Now please remember this theta 1 equal to THI minus TCI and theta 2 equal to THO minus TCO. Okay, and you can use either delta T1 or theta 1, whichever is comfortable for you. Okay, in all cases, for the numerical purpose, I will be using the theta 1 and theta 2, or if you want, you can use the delta T1 or delta 2. That hardly matters. But remember, this is at the inlet and this is at the outlet. The key of this derivation lies with number one. Number one is the initial equations of the heat duty. Then finally, this minus is reduced to this plus. Means we are reciprocating this logarithm. x2 by x1 is equal to minus x2 by x1. That is the meaning of it. I'm sorry, it should be equal to ln of x1 by x2. I repeat, minus ln of x2 by x1 is equal to ln of x1 by x2. That is the meaning. Okay. Is it clear? Okay. Now question comes, this is for the parallel flow. What about the counter flow? Okay. Yes, you are very right. What if the parallel flow is there over, then what about the counter flow? Okay. The derivation is very similar to that of parallel flow. Okay. But there is a small difference between these two. Okay. So this is the, suppose the parallel flow, I am taking this one as x, whereas in counter flow I am taking in the other way. Okay. So let me say this is the hot fluid. This is the sorry. So this is the THI and this is the THO, whereas this is the TCI and this is TCO. Remember, the profile changes, but the LMTD formula won't change. So here it is, let me say theta 1 and theta 2 only. Okay, it won't changes with respect to the flow, but the derivation has got little things to do. So when you talk about the Q, okay, when you talk about the Q, it will be surely UA delta Tm or LMTD. It won't changes. Okay, in the hot fluid also it won't changes, but when you talk about the dq and the dq for hot fluid, then in both cases it will be mh ch into dth, and this is minus mc cc into dth. This is for the counter flow heat exchanger. This is for the counter flow heat exchanger, because if I take a x, then if I take the difference between these two, okay, then in the direction both will be negative. That is the only difference. Then the rest will be as it is same. Rest will be as it is same. Even when we are talking about this minus, it will come almost all same, but the initial step only changes. So this is the parallel flow and this is the counter flow. For the parallel flow, the derivation has been done, and counter flow you are advised to do on the same lines. Okay. So remember, in the parallel flow and the counter flow, initial the heat exchange, heat duties are same, but the differential when we write, it will change because the temperature profile changes. So here only the heat loss losing or the hot fluid only will have the negative sign for the parallel flow, whereas for counter flow it is in the other way, means both will have the negative signs. Based on that you are advised to derive it. Now question comes, sir, what about the okay, just a minute. Now question comes, sir, what about the numerical part? Yes, numerical part we are going to take it, but remember the formulas. However, there is a one piece of advice. Okay, if you refer to the your data handbook, page number 151. Okay, 151. The notations used are little bit different. Okay, it has not been used as please wait for a minute. It's okay. So this is for this is for parallel flow, whereas if I coming for the counter flow, what we have shown. So in this case, the hot fluid is going from the left to right, whereas the cold fluid is going from the right to left. In both cases, they will have the negative temperature difference. Okay. Now the next one what we are discussing is nothing but the special cases. There are certain special cases are there in case of a condensing fluid. So whether it is a parallel flow or the counter flow doesn't make any difference, because the delta T1 and delta T2 are same. Why? Because delta T1 and delta 2, whether you take from the counter flow or the parallel flow, it makes no difference. Okay, because one fluid is same. Condensing means at a one temperature. Let us say in a steam power condenser, it condenses at a 45 degree centigrade. So whatever the 45 degree centigrade steam is there, that will be converted into 45 degree centigrade water. Okay, whereas the cooling water will surely heated. Whereas the second one, in case of the evaporating, in case of the evaporation, it is the other way. So the cold fluid won't change its temperature. Okay, in that case, whether it is a parallel flow or the counter flow, hardly makes the difference. Last one is very important, where the CH and CC. So what is CC? Remember the MC into CC and MH into CH. This is called as a heat capacity. If both heat capacities are equal, then the delta T1 equal to delta T2. In our terms, it is a theta 1 equal to theta 2. In those cases, you have to take the average of the both one. Means what? Delta T1 plus delta T2 divided by 2 you need to do for such cases. Okay. So today we have discussed about the heat exchangers. What is a heat exchanger? What is the concept? Okay, what is the classification? What are the different terms used? The most important terms will be overall heat transfer coefficient, then LMTD, then next one is the fouling factor. Now questions, that's all. Anything new you have got? Yes, we have got some new, some other terms also, such as the NTU and effectiveness, that will be seen in the next class. Okay, but however, the thing, please remember, in a derivation, if you pick up any question paper of any university, out of 10 question paper, I feel minimum 4 to 5 times this derivation has been asked. Means either parallel or the counter. Okay, parallel flow LMTD or counter flow LMTD is asked. You can check up with your university question paper or the previous question papers if they are available on the net. With this one, we are stopping for the day. But remember, this derivation is very simple and comfortably can be done. Okay, even if you go with the question paper, okay, if you go with the question paper, the classification has been asked, the terms have been asked, such as the fouling factor and other things, that you need to get it perfect, so that in exams you will get the full marks. Okay. Now question comes, sir, what about the next class? In the next class, we are going to do a few problems on the parallel flow as well as the counter flow, including the cross flow. Okay. Then we are going to discuss about the NTU method. After the NTU method, we will discuss some more problems on the question papers of the previous question papers of the previous year. Okay. With that one, signing off for the day. We will see in the next class as soon as possible. Thank you. Good day.